first let us understand the relational operators. So relational operators are basically the greater than, the lesser than, the greater than or equal to, and the lesser than or equal to. So these are the four relational operators in Verilog. Relational operators basically checks the relation between the two numbers and it just returns either a logical value of 1 if the relation is true or a logical value 0 if the expression is false. So it checks the relation. If the relation is true, it sends logical 1. If the relation is false, it sends a logical 0. And in case if there are any unknown bits or the high impedance bits in the given number, then the answer will also be unknown, because without a bit value known, it is difficult to tell the relation between the two numbers. So if any input has an X or Z bits, the result in this case will be unknown. Let's see some examples of relational operators. So let's take A equal to 4, B equal to 3. Let's take two more numbers, X equal to 4-bit binary 1010 and Y as 4-bit binary 1101 and Z as a 4-bit number 1XXX having unknown numbers in the last 3-bit positions. Let's check the relationship between these numbers. So the first relation, A less than or equal to B. Is 4 less than or equal to 3? No. So this relation is false. So false means it evaluates to a 0. A logical 0 is the answer. Next, A greater than B. Is 4 greater than 3? Yes, it is true. So when the result is true, it evaluates to logical 1. Y greater than or equal to X. So Y is 1101 and X is 1010. So this is 10 and this is 13. Is 13 greater than or equal to 10? Yes, it is true. So this also evaluates to logical 1. Y less than Z. Y is 1101. Z is 1XXX, unknown number. So without these bits known, it is difficult to predict the result. So the result here will be a logical X. That is, it evaluates to an unknown value. The next class of operators we are going to study is the equality operators. So Verilog has four equality operators, namely the logical equality, the logical inequality, the case equality and the case inequality, with their symbols are shown here. Now, just like the relational operator, equality operators when used in an expression, it will return a logical value of 1 if the expression is true. If the expression is false, it returns a 0. So these operators basically they will compare every bit of the operands. So two operands which are being compared, they are compared bit by bit, and in case the operands are of different size, then they are 0 filled on the MSB side to match the sizes. So let us see the examples of equality operator. So A double equal to B means it checks if A is equal to B. The result can be unknown if X or Z is in A or B. So if either of A or B inputs has an X or a Z bit, the result will be X or Z. Meaning to say the possible values of this output is either a 0. We can get a 0 if A is not equal to B. If A is equal to B, we will get the answer as 1. And if the result is unpredictable because of X or Z bits, we can get an answer as X also. Similarly, A not equal to B. So when we compare A not equal to B, if A is not equal to B, it is true, then we will get a 1. If it is false, we will get a 0. And if either A or B has an X or a Z bit, then the result will be unknown. The difference you can observe here is, in a case equality and case inequality, this will compare A and B including the X and Z position. If the X positions are matching, the Z positions are matching, it will just tell whether they are perfectly matching with the X and Z or whether they are not matching. So here in case equality and inequality, it will include even the X and Z bits. It will check if they are matching perfectly or not matching perfectly. So in this case, we will not get an unknown output. We will get either a 0 or a 1. So we can observe this and understand with an example. Let us assume A is 4 and B is 3, and let us take X and Y as 4-bit binary 1010 and Y as 4-bit binary 1101. Let Z be 4-bit binary 1XXZ, M as 4-bit binary 1XZZ, and N as 4-bit binary 1XXX. So we have taken all X and Z combinations here. First, let us check if A is equal to B. Is A equal to B? No. So the result is a false value. So it evaluates to 0. It gives us logical 0. Is x not equal to y? So compare x, which is 1010, and y, which is 1101. Are they not equal? Yes, they are not equal. So this will result in a true, because this condition is true. X is not equal to y. The expression is true. So it results in logical 1. X equal to z. So here x double equal to is logical equality. So every x and z bits means the result will be unknown. So 1010, 1xxz, it's difficult to predict. So it will result in logical x, right? We're going to get an unknown value. Let's see now examples with the case equality operators now. So in this case, let's take the same examples that we had previously taken. Now the first one tells, is z triple equal to, so this is a case equality, is z equal to m? Check out what is z. It is 1xxz. What is m? 1xxz. Now this is a case equality because there are three equal to signs. So are they perfectly matching? You have 1xxz equal to 1xxz. So every bit position is matching. You have 1 and 1 here, x and x, x and x, z and z. So are they perfectly matching? Yes, they are matching. So this results in logical 1. All the bits are matching, including the x and z. So you can observe here, in case equality we include x and z. But in logical equality, inequality, if there is x and z in the numbers, input numbers, the result will be an x. So in this case, we will never get an x. If they match, you will get logical 1, that is true. If they do not match, you will get a logical 0. Z equal to n. Compare 1xxz. Is it equal to 1xxx? They are not matching. The last bit position is z here and here it is x. So we are going to get a logical 0. So in this case, it results in logical 0 because the least significant bit does not match. M not equal to n. So we have not equal to 2 equal. So this is case inequality. We have m is 1xxz and n is 1xxx. So it is telling m is not equal to n. Yes, it is not equal to. So it is true. So it results in logical 1 again. Now we have bitwise operators in Verilog. So the bitwise operators in Verilog are the negation operator, which is the unary operator, the AND operator, the ampersand, the OR operator, the pipeline operator, the XOR operator, the caret symbol, and the XNOR operator, which is a combination of XOR and NOT, which can be written in either of the two ways. The bitwise operators perform a bit by bit operation on the two operands. So unlike logical operators, which was taking the logical value of the number, bitwise operators, as the name suggests, they perform these operations on every bit and will give us the final answer as the total size of the basic input size. So they will take each bit of the operand and it will perform the operation with the corresponding bit in the other operand. And in case one operand is shorter than the other, then zeros will be filled to match the length of the longer operand. And if there is any z in the given input number, it is treated as an x in a bitwise operation. So let us see the logic tables of the bitwise operators. So the simple bitwise AND, so we can check here, 0 and 0 is a 0, 0 and 1 is a 0. Anything ANDed with 0 is a 0. So this row and this column turns out to be 0. 1 and 1 is 1. Anything with an x is an x. So the rest of the column will be x. Bitwise negation, which is the NOT, 0 is 1, 1 is 0, x is an x. Bitwise OR, so wherever we have a 1, the output will be a 1 for the OR gate, 0 or 0, 0. For the rest of the cases where one of the input is unknown, the output will be unknown. Similarly, bitwise XOR. So here, when the inputs are different, we have the output as 1. So 0, 1 is 1, 1, 0 is 1. For when the inputs are same, 0, 0, the output is 0, 1, 1, the output is 0. And when any one input is an x, the output is an x. Similarly, bitwise XNOR is the complement of the bitwise XOR. Let us see bitwise operators example. So let's assume x is a 4-bit binary number 1010 and y is a 4-bit binary number 1101 and z is a 4-bit binary number 10x1. So first operation is not of x. Not of x means complement every bit of x and just write the result. So x is 1010. So when we complement this 1010, we are going to get a 0, 1, 0 and a 1. So the result will be 0, 1, 0, 1. It's a negation. So we are going to get all the bits of the given input number inverted. Next case, x and y. So we have to take x, which is x value given, the given input number is 1010. That should be ANDed with 1, 1, 0 and 1. So when we AND this, we are going to get a normal AND gate operations. So 0 with 1 is a 0, then 1 with 0 is a 0, 0 with anything is a 0 and 1 with a 1 is a 1. So this is the answer we have to get, all the 4 bits. Every bit is odd, that is the bitwise operator. So we are going to get the result as 1, 0, 0, 0. Similarly, x or y. So OR gate gives us a high output when any one input is high. So we can observe here we have 1, 1, 1, 1. So the result will be 1, 1, 1, 1. X XOR y. So XOR will give us a high output when the inputs are different. So we can observe here, so for these three cases we will get a high output. So the answer will be 0, 1, 1. 4-bit binary 0, 1, 1. X XOR y is the complement of this output. So we have to get 1, 0, 0. And x and z. So in this case we can observe we have an x in this bit position. So when we AND these two input numbers 1010 with 10x and z, in this particular bit position number we have an x. So we have one ANDed with x, the result will be an x. So the expected answer for this case will be 10x0. 10x0 is the answer. So every bit must be ANDed or ORed from the bitwise operation and we have to obtain the result. So in this video lecture we understood about the relational operators, equality operators and the bitwise operators in Verilog with an example. Thank you.